So this is some help with question 16 from Sapling Learning Chapter 6-1. So this is a problem that we began working in class, but I need to tell you a little bit more about the second part of the problem. Thinking about the first part of the problem, I wanted to point out a couple of things. So we're asked to calculate the concentration of IO3- iodate in a 3.34 millimolar lead nitrate solution that's saturated with lead iodate, PbIO32. The solubility product constant of PbIO32 is 2.5 times 10 to the negative 13th, so it's relatively insoluble. So we're asked to assume that the lead iodate is a negligible source of lead ion compared to the lead nitrate. Okay, so what's going on here is we're making use of a solubility rule that tells us that all nitrate-containing compounds are very soluble in water under normal conditions. So lead nitrate solid, when you add it to water here, is going to almost completely dissociate into its ions to give you lead 2+ and 2 nitrates. At least it will break apart, and at least it will dissolve. It may form some ion pairs and that sort of thing, but we're going to imagine that it just does this. Alright, so we're going to say that its equilibrium constant is much, much greater than 1. So we can assume that essentially 100% of this lead nitrate solid is going to dissolve to give us lead ions. So if we have 3.34 millimolar lead nitrate, then we see from the stoichiometry that one molecule of lead nitrate dissociates to give us one lead 2+ ion. So its concentration is going to be 3.34 millimolar. Now when lead nitrate breaks up, we're going to get 2 moles of nitrate for every one of the lead nitrates that dissociates, and so that would mean the concentration of nitrate is 6.68 millimolar. But we don't care about the nitrate concentration in this problem. It's what we call a spectator ion, so it doesn't participate in reacting with the iodate at all. So then what we needed to do is write down what our reaction is, our solubility reaction, with lead iodate. So lead iodate dissolves to give you lead ions and iodate ions, 2 moles of them, and our KSP, our solubility product constant, is this expression right here. Concentration of lead times the concentration of iodate squared. So it turns out that we know KSP, and from this first problem right here, we know what the lead concentration is in our solution. And so like I talked about in class, we just need to solve for the iodate concentration. So I'm going to scroll down here and we're going to write an equation to do that. So we're going to just solve that equation for iodate, IO3-. So we divide both sides by the lead concentration. So KSP gets divided by the lead concentration. And then we would have the IO3- concentration on this side squared, so we need to take the square root of both sides. So this is going to be the square root, which is the same as raising it to the 1/2 power. So that's going to be the iodate concentration. And so you're just going to plug in your values for KSP and lead. Remember that when you plug in the value for lead, it's 3.34 millimolar, or whatever your number may be. Your mileage may vary. And remember that millimolar, we need to plug in our concentrations in molar, because thermodynamic equilibrium constants are based on having concentrations in units of molarity. So we're going to need to convert that 3.34 millimolar into molarity, and that's easy to do, just remembering that the milliunit here means times 10 to the -3rd. So remember, when you go and substitute the lead concentration in here, it's 3.34 times 10 to the -3rd molar, or millimolar. Okay, so that was the first part of the problem that we worked this morning. Now we want to do the second part of the problem right here, and it turns out it's a little bit more complicated than what I talked about this morning. So it says a different solution contains dissolved sodium iodate. So here's another solubility rule for you. All salts of group 1A metals are soluble. So group 1A, that's the first column of the periodic table, and so sodium is in that column, and we're thinking about sodium iodate. So that's going to tell us that our sodium iodate is going to be completely soluble in water, essentially. And so we're going to imagine that all moles of my sodium iodate compound dissolve to give us sodium cations, which we don't care about, they're just spectator ions, and iodate ions. So this is then a source of iodate. And so it asks us, what is the concentration of sodium iodate if adding excess lead IO3 solid produces a lead concentration of this much? So again, we know our lead concentration. There is only one iodate concentration in our solution, so we can find that. And so that's what I talked about this morning. So we kind of worked the problem the same way. So we're going to find our iodate concentration. Knowing our KSP value, that's the same, and we're going to divide by the lead concentration, which we were given in our problem, and we take the square root of that whole thing. So that will give us the iodate concentration. Right? So that tells us what the iodate concentration is in the solution. But we're asked to find the NaIO3 concentration. So how many moles per liter of sodium iodate did you add to the solution if it produces this lead concentration? And it turns out that iodate has two sources. So we're going to write an equation for those two sources. So iodate comes from two places. It comes from the sodium iodate that we added to the solution, but it also comes from the dissolution of the lead iodate. So some of that lead iodate will dissociate to give you lead ions and iodate ions. Right? So we have two sources of iodate. So the total iodate concentration, IO3 minus, is going to be equal to the concentration that we get from the sodium iodate. And since 1 mole of sodium iodate gives us 1 mole of iodate, we can just think about the molarity of the sodium iodate as being added in here. So 1 mole of sodium iodate has 1 mole of iodate in it, and so that's where we're going to get that iodate. Then we need to add in here the amount of iodate that we get from this dissociation. And what do we notice from stoichiometry? Well, from stoichiometry, we see that we get 2 moles of iodate for every 1 mole of lead that appears. So we can simply say that this is going to be plus 2 times the lead ion concentration, Pb2+. Okay, so from solving this first part of the problem right up here that I'm putting the arrow beside, we know the iodate concentration. That's what this term is right here. Right? So we know that. What we don't know, what we're looking for, is the sodium iodate. So what is the concentration of the sodium iodate? We actually know the lead concentration because they told us that in the problem. So now all we need to do is solve for our unknown using the things that we know. So the iodate concentration we can calculate up here using the KSP value and the lead value. We know the lead value here, so we just subtract that. So let me scroll down one more time and give us a little bit more space to write out sort of the final formula that you would need to calculate this answer. The sodium iodate concentration is going to be the iodate concentration that you calculate from the KSP minus 2 times the lead concentration that was given in the problem statement. So that's a sketch of how you would finish working this problem.